Hi, this is me trying to solve the second question in Sierpinski's book, 250 Elementary Problems in Number Theory, in Lean. And in some sense, I cannot solve it. I tried this one in advance, um, and there are problems here. And let me show you the problems. So first, let me tell you the maths proof. The question is, I want to find all integers x not equal to 3 such that x minus 3 divides x cubed minus 3. And I don't know why Sierpinski left out the case x equals 3. Because if x equals 3, the question is asking whether 0 divides 24. Maybe Sierpinski for some reason thought that was a confusing question. But I mean, I know the answer. 0 does not divide 24, right? Because there doesn't exist an integer t such that 0 times t is 24. So I don't quite understand why we demand that x is not equal to 3, because 3 doesn't work. So let me show you the maths proof. It's very similar to the previous example. So here's the solution, my solution. X minus 3 certainly divides x cubed minus 27, right? Because I mean, it's the linear root test or whatever it's called. 3 is a root of x cubed minus 27 equals 0. So x minus 3 divides it. And if you think about it carefully, you'll see that the quotient is what, x squared plus 3x plus 9, which is going to be an integer as well. So and hence if it divides x cubed minus 3, and then it also divides the difference, right? Which is 24. And then, of course, conversely, just the same thing, right? If x minus 3 divides 24, if x minus 3 divides 24, then because it divides x cubed minus 27, it also divides x cubed minus 3. So if you like, we could do this, right? Example, I'm claiming that this is x is an integer. I claim that x minus 3 divides x cubed minus 3 if and only if x minus 3 divides 24. And that should be relatively straightforward. I think we're going to have to split it. And now this one is whatever, intro h, blah, and this one is, sorry, intro h, so what do we know? Oh, what we know is that we have no output. Where's my output? The output has gone, so let's restart Lean. See if the output comes back. Oh, how about I put my glasses on there and notice that I'd used the wrong brackets. So why is this true? Do you know what? Both of them, I think, well, before we split, we want to do this, right? Have h. I claim that x minus 3 divides x cubed minus 27. And the proof of that would be, remember this just says there exists an integer y such that x minus 3 times y is x cubed minus 27. So I'm just going to use x squared plus 3x plus 9. And then the ring tactic will do that, right? Well, we can't tell it's done it because I didn't do the correct thing. There we go. Let's do that there. So indeed, the ring tactic did do that. So now intro h. So now what let's call it something else. Let's intro h1. So we know that it divides x cubed minus 3 and x cubed minus 27, and we need to deduce it divides 24. So this will be divud sub or something, right? So have h2. It'll be divud. Yes, indeed, it's called divud sub. Divud sub says if a divides b and a divides c, then a divides b minus d. So this slash symbol is called divud in Lean. And so the names of the theorems about this symbol will be called divud. Well, they'll mention divud DVD in the title. So what am I going to do? I'm going to put in H1 and H2, right? No, I'm going to put in H1 and H. And now I claim that the answer is H2, right? X minus 3 divides. This simplifies to 24. So one way we could do it was we could run the non-finishing ring tactic on H2, and then it's exact H2. That would be one way of doing it. Or alternatively, we could use the convert tactic, because H2 is the right answer, right? H2 is a proof of this theorem, except it's not it's not quite. I'd like to put exact H2, but lean's like, well, no, this isn't definitionally equal to 24, right? It is equal to 24, but it's equal to 24 because of a theorem. So I can't put exact H2, it doesn't work. Exact works up to definitional equality. So I can put convert H2, and that will leave us with the claim that 24 is what I'm claiming it 24 is, and now the ring tactic can do that. So that's one way of doing that way. And this way should be just as easy. So intro H2 or H1. And now my claim is that if x minus 3 divides this and x minus 3 divides this, then it divides their sum, right? So this is going to be, I can just do convert. It's going to be called divert add, right? Divert add H1. And again, I can just use the ring tactic. So there you go. So Lean can certainly do that, but in some sense I haven't answered the question, right? Because I haven't actually said what the divisors of 24 are. So I would be able to finish this question if I could prove the following thing, right? Example, let's have A, an integer. I claim that A divides 24 if and only if A is in the following set, right? Minus 1, minus 2, minus 3, minus 4, minus 6, minus 8, minus 12, minus 24. And then plus 1, plus 2, plus 3, plus 4, plus 6, plus 8, plus 12, plus 24. And Lean is complaining. Lean doesn't have a clue. Yeah, Lean doesn't have a clue what these are. It's like, are they numbers? Are they natural numbers? You're negating a natural number. That's not even. Lean needs to be told that this is a set of integers. So that's my interpretation of that error message. So let's do that. There. And this is exactly not the kind of question that Lean was set out to do. This is a calculation, right? This is the kind of thing a computer algebra package would be able to do, work out the divisors of 24. And I don't know how to solve this. I tried a bit in rehearsals. I mean, the thing. I mean, here's one thing you could do. We could do have H1, A is less than or equal to 24. Oh, so wait. Let's split it. Sorry. There. This one, that's the hard one. Let's talk about the easy one. So if A is one of those things there, then A divides 24. So, I don't know, intro H. This is just a massive OR statement. This is definitionally A is -1, or A is -2, or A is -3, or blah blah blah. And so you could do R cases H with ruffle or ruffle or ruffle, this sort of thing. Let me just show you what's happening here. You see that we're getting more and more goals, and these goals here, because they've got numbers, they can be solved with norm num knows about division. So norm num, you see, norm num just solved from the goals, 3 goals, 2 goals, 1 goal. You see. So ruffle, that's 1, 2, 3, 4. Or let's copy the space. That's 8, that's 12, and that's 16. Now let's get rid of that one. Oh, is that? Yeah. No, yeah, it didn't quite do the last one. I think that's definitionally A is 24, but somehow Lean didn't spot that. So anyway, now we've got 16 goals. But one nice trick is you can put a semicolon, and then norm num doesn't do the last one. And now we can put try norm num. The semicolon means do the next tactic to all the 16 goals. I mean, the semicolon means do the next tactic to all the things produced by this tactic. So we could try norm num, and now we've only got one goal left. And yeah. The substack. Is that not true? I want to. What? I claim change. I might be wrong. Change A equals 24 at H. No, this is definitionally. There we go. Rewrite H, and then I was gonna use wow. Oh, I see. It tried REFL and Lean knew that division was reflexive. So that's that way round, and this way round I can't do. I mean, this was the idea I had. So intro H. So have H1. I claim that A is less than or equal to 24. And why is A less than or equal to 24? It's because, I don't know, let's try library search. I think, do you know what? I think library search won't work because this isn't always true, right? If A divides negative 24, then A isn't less than or equal to negative 24 because it could be 2. So we need the hypothesis that 24 is positive, right? So let's go with this. Less than 24 by whatever. I mean, let's just sorry it. And now let's try library. Now, I've put the key. Yeah, you see, now it works. So it's there we go. Now we know what it's called. It's called int Ellie of divd. So this is colon equals int Ellie of divd, and then we need a proof that 0 is less than 24. So that's by norm num, and then I'll just put an underscore just to check that we've got everything right. And now we need to prove that A divides 24, and so that's H. So we've got A is less than or equal to 24, and now I also claim A is bigger than or equal to negative 24. I wonder if that's actually there. Let's have H2 back. 0, the integer Z is less than 24 by norm num. And now can I deduce have H3? I claim that A is greater than or equal to, well, minus 24 is less than or equal to A. That Lean doesn't have any results in the library with greater than or equal to. And does library search do this? It should be called no, it doesn't. That could be in the library. There you go. If anyone wants to make a PR to the library. Okay, so we're going to have to do it the boring way. So I claim. I mean, we don't need this. We can do this by norm num. So have H2. The point is, I claim that negative A divides 24. And it doesn't like it, so no, I need to put it in brackets. Oh, I did the wrong kind of divide. I probably didn't need to put it. Let's remove the brackets. Yeah, there you go. I put the divide that looks exactly like the other divide, but I put that instead of that. The identical version of that. So I claim that if A divides 24, then negative I divides. That's going to be called like neg divd or divd neg. Library search. Let's find out which one it is. It's called neg divd. There we go. And so now, of course, we can get to have H3. I claim that negative A is less than or equal to 24. And that's going to be the same proof. But this time, instead of feeding it H, we'll feed it H2. And so now have H4. I claim that negative 24 is less than or equal to A by Lillerith. There. So now you see, we know that A is less than or equal to 24 and A is greater than or equal to negative 24. And so we know there's only 49 possibilities for A. And so the way to continue now would be interval cases. Interval cases A. And then we'd get 49 cases. And in those 49 cases, we would either prove that A was in the set, which is what we wanted to do. Like for some of them, A is in the set, and that's the goal, and so we could just do it because A will be a number. But for the other ones, our goal will become false, right? A goal will be something like 15 is in the set that doesn't contain 15. But we'll have a hypothesis that 15 divides 24, and that will be false as well, and norm num will be able to do that for us. But you see what's happened here is that Lean has timed out, a deterministic timeout. So interval cases have somehow failed to give us the 49 cases we wanted. And that's just, hard luck. 49 cases is really quite a lot of cases for in my experience, I normally have 1 or 2 cases. And so what we really need, we shouldn't be doing this at all, really. There should be some tactic that does this for us. But that tactic needs to be written by a computer scientist somehow. And so I'm not going to write it. And so that's where I got stuck on this problem. And it would be interesting to know if the other theorem provers can do it. Koch and Isabel Hall are both very good at calculations, so it wouldn't surprise me if they could solve this goal. But there we go, we're struggling in Lean 3. Bring on Lean 4. Thanks for watching.